I'm Joshua on the diffusion model project. So diffusion models are a class of deep generative models designed to create high-quality images. During training, we start with real images and gradually add Gaussian noise to them. This is called the forward process. Eventually, the images become completely unrecognizable, almost like pure static. The model then learns to denoise these images step by step, reversing this process until it reconstructs something realistic. For this project, we trained on the ImageNet 100 dataset, which contains about 130,000 images covering a wide range of classes. This diversity makes it a strong benchmark for evaluating generative performance. Our approach builds on several key components in the diffusion modeling pipeline. We begin with DTPM, which learns the reverse diffusion process. The model takes noisy samples and uses a U-Net to predict the noise that was added at each time step. This gives us a very high quality outputs, but the drawback is that the inference is slow. To address this, we incorporate DDIM. This allows us to generate image in fewer steps, giving much faster inference while keeping the sample quite comparable. Next, we move from operating directly in pixel space to latent diffusion models. By encoding image into a compact latent space using VAE, we drastically reduce the dimensionality of the diffusion process. Finally, we apply classifier-free guidance, CFG. It lets the model interpolate between unconditional and conditional predictions during inference. This provides much stronger control over what the model generates and leads to better semantic alignment with the intended class.
Moving on to our experiments, we trained our models on the ImageNet dataset provided by the teaching staff. We trained the DDPM, DDM, and VAE models for 500 epochs to ensure fair comparison. For evaluation, we looked at FID and IS. On this slide, you can see our DDPM baseline achieved an FID at 3.342. However, if you look at the samples on the right, there is a clear disconnection between the metrics and the visual quality. While the model has learned the correct color patterns and textures of ImageNet, the generated images are not clearly recognizable objects. On the next slide, we compare this to the results of DDM and VAE. The DDM model achieved a slightly higher FID of 4.067. Visually, it suffers from the same issues as DDPM. The symbols are noisy and difficult to interpret. The VAE shown at the bottom represents an interesting case. It achieves the highest inspection score of 7.27, but the FID spiked to over 26. Despite the higher IS, the VAE images are even further from reality than other diffusion models. Moreover, our results show that where we achieve static convergence with reasonable FID scores, generating clearly recognizable coherent objects remains a challenge for all three architectures in this setup.
Often learn generic animal-like features, but they were messy and frequently missed class-defining structure. Once we enabled CFG, we started getting clearly classifiable images at around 150 epochs, and by the end, we saw strong results across a wide variety of classes. For example, birds and spiders were two of the earliest to stabilize, which makes sense because of the high contrast. However, CFG was also especially valuable for harder low-contrast categories, for example for aquatic classes, where guidance helps reinforce semantic shape cues even when texture cues are weak. We used a mild guidance scale of S=2 for our CFG training parameters to strengthen class fidelity without excessively sacrificing diversity. Following the improved DDPM SQL research paper, the cosine scheduler is preferable because the linear schedule adds noise way too quickly early on. A cosine noise scheduler keeps the signal to noise decay smoother, so more of the diffusion trajectory remains informative, instead of spending many compute steps comparing random noise to random noise. In our results at around 150 epochs, plain CFG achieves FID of 6.85, while CFG and cosine is a lot worse. However, because we used 4,000 training time steps instead of 1,000, a larger T spreads learning across many more noise levels. So each time step gets fewer effective updates and convergence is going to be worse early on. So I think this initial result is mainly because of limited compute, not that cosine scheduler is intrinsically worse. Out of all our ablations, CFG gave our strongest class fidelity and overall sample quality, but was very costly. For CFG, we trained at 500 epochs for over 200 hours, using 3 B200 GPUs and spent over $1,000 in compute. This means we need to spend more time on efficiency-focused improvements instead of just distant metrics. For example, we could spend more time on better noise schedulers and adaptive and dynamic guidance. Even though Stable Diffusion achieves better efficiency through latent space, in our setup, the pre-trained VAE was our bottleneck, which heavily limited the gains we could have gotten from latent DDPM without heavy modifications to our starter code base.